Hello everyone and welcome to our talk on latent temporal flows for multivariate analysis of wearables data. I'm Magda Miridi and this work was done in collaboration with Greg Darnell and Sean Jewell from Apple Health AI. In this work, we introduce a new method for multivariate forecasting tailored for cases where we have a large number of complex and statistically dependent time series. Modeling multivariate time series finds a wide range of applications, especially in the area of healthcare. Machine learning models applied on data collected from wearable devices can be used to build insights into an individual's health and develop a real-time tracking system for deterioration in a patient's health status to facilitate early intervention. For example, data collected from wearables have been used to detect COVID-19 symptoms or influenza infection in asymptomatic people or the common cold with high accuracy. Our application of interest is to produce 20-day multivariate forecasts of vital signals given 30-day observations of daily heart, blood pressure, and physical activity measurements. One could leverage this information to detect abnormal events or to recover hidden causes. Classical methods can handle only one data variable at a time, or at most a few dimensions, or require restrictive assumptions. But the complex nature of healthcare data necessitates an expressive multivariate tool to provide greater insights into an individual's health, as complex high-order dependencies in sensor signals have been shown to be associated with changes in physiology. We aim to learn dynamics in a complex low-dimensional space to enable faster forecasting and potentially reveal latent trends. Our model consists of three key components: an embedding mapping G, a latent conditional distribution of temporal transitions, and the recovery function Q. Mappings G and Q are trained through a deep autoencoder network, while latent transition dynamics are learned using a combined structure for normalizing flows and the multivariate recurrent neural network. In this way, the proposed model increases parsimony while reducing computational complexity. The optimization process is guided by two sorts of losses: the reconstruction error term and the negative log likelihood loss. A joint optimization is pursued to favor latent representations that uncover dynamics over future state. We evaluate the empirical performance of our method on the Apple Heart and Movement dataset, which contains daily signals collected in real-world environments, which constitute a measure of cardiovisual and autonomic nervous system activity, as well as movement and activity metrics. Using the normalized mean square error, we assess the test time signal predictions produced by our method and compare against existing classical methods, showing that on average, latent temporal flows with dimensionality 5 achieves the best signal predictions. In these figures, we demonstrate the quality of predictions produced by the proposed model in the future 20-day window over a randomly chosen individual. To reveal the underlying factors controlling accurate forecasts, we visualize 2- and 3-dimensional representations across 50 time points for 8 different individuals belonging to 2 disjoint cardiorespiratory fitness levels. The latent representations for both t equals 2 and 3 indicate that the mapping learned by the optimization leads to a space with easily visualized clusters that well separates individuals according to VO2 max. Additional experiments on 5 publicly available datasets further support the accuracy of forecasts produced by our model against well-known baselines. In this work, we presented a novel method for multivariate forecasting of complex time series and studied a challenging practical application of predicting sensor signal trajectories. While here our focus is on time series forecasting, future work will extend our framework to other tasks such as detection of abnormal changes in the health of individuals. Thank you very much for your attention.